Okay, thank you very much. So I'm going to be joined here by Brent Brunel as well. And what we'll try to do in this first half hour is to give you a view of GE's journey across industrial AI, talking about how we use this capability to drive business value, but more so, how do we combine software and hardware AI capabilities at the edge to deliver this value. So let me start by motivating why we're doing this. So if you think about the world we live in right now, we have a significant install base, trillions of dollars of install base. You look at the jet engines we have 70,000 commercial and military engines. At any given point in time, 300,000 souls are in the air at any moment. We have to care and protect these souls. We generate a roughly 1/3 of the world's electricity. And at any point in time, again, every minute, we do 16,000 scans on the human body. That's a significant installed base providing social value throughout the planet. But with that, to our customers comes the need to provide that financial acumen that keeps these things running. So we have 4 drivers we look at all the time. How do I get better productivity of the assets you have? How do I find ways to generate more revenue? How do I do it in a way that can manage business risks as the world changes? And how do I do it safely? The trick now is not to do 1 or 2 of these things, but to do all of these things together. Then underlying that, you have certain dynamics that are happening. The first one is the customers. We are now not only dealing with our customers, but our customers' customers. So I'm not only dealing with the airline companies, I'm also dealing with the people who fly on the jets. Because if they don't fly on the planes, there's no revenue from the stream. You're not only dealing with the people who you give the electricity companies that you give these turbines to, you're dealing with their customers. They like to know that they're getting renewable energy and how they manage it themselves. Added to the focus now on the customer point, we also have to look at the actual landscape that's competitive. We see new competitors emerging. We're accustomed looking at the competitors we know in our space, but new ones show up. Take a look at Amazon, for instance. Amazon, well known in retail at this point in time, but also Bezos in 2000 created a company called Blue Origin that builds rockets. Right? So he invested $1 billion until 2011. From 2011 onwards, he did $1 billion a year. He just won last year. The actual BE-4 rockets were chosen for the Vulcan program. Vulcan is the combination of Lockheed and Boeing. That's the new rocket that they have that's reusable. So he is now in aerospace. Elon Musk has gone from PayPal into aerospace, into SolarX for electricity, now into Boring Company as well as Tesla. New competition emerging from very different places. Also, the impact of tariffs, governments having significant impacts. So those are the dynamics. But even more important is this last one here of the digital capabilities. So we've watched the world evolve from digital allowing humans to engage with information, humans engage with services, humans engage with other humans, to now humans engaging with machines. And machines engaging with machines. You see the wind turbine there, actually, we have a robot that's actually inspecting the wind turbine. So all of these are the dynamics that are happening that are driving the financial drivers to an installed base that's on this planet for years to come. These engines last anywhere from 20 to 40 years. So how do we use AI to actually allow us to meet these financial drivers? So what we did, we spent some time looking at the consumer space. That space that has been using AI for a number of years, and we decided, let's figure out the best practices, let's take those, let's evolve them, let's innovate around them for ways that GE could use them. So we started and we analyzed this thing about 6-7 years ago, discovered there were 3 companies doing some very unusual work that made them leaders, but they're all using the same method of digital transformation. This is Amazon, Apple, and Google. So you look at the revenue numbers, because when you look at leadership, especially in the business sense of the word, you want to look at revenue at the start and market share. You look at the revenue numbers, it's interesting. You look at Apple, you see them at roughly 265, Amazon 236, Google $135 billion a year. They range from 22 years old to 42 years old. It took GE 102 years to get to $100 billion. Look at the rate of growth of these companies, all using the same method. I'll just use Amazon as an example here. So this is the technique Amazon uses, but they all use the same technique. It starts off by creating a model of one. Amazon started off by trying to get data on groups of people, demographic data, right? If this group likes this book, then maybe I can actually say that you would like this book as well. They quickly went from demographic data or to data on an individual. Rather than groups, an individual. They looked at what you bought, when you bought, what ads you looked at, what reviews you looked at, what you did on Mother's Day, Father's Day, where you sent the information. They collected all of that. They collected information on you, all 300 million of their users, and created a psychographic model, a model on how you buy and when you buy. With that model of one, they then actually applied AI. So they're looking at things like segmentation. If you belong in this segment, and this segment has a book, let's offer you that book at a discount. They looked at prediction. If I see you looking at these ads and these product reviews, then let me offer you these skis at a discount. If you buy the skis, they then did, profiling. If you buy these skis, I can then predict, after I've profiled you, that you're going to want a helmet. So I offer you the helmet at a discount. So with segmentation, profiling, and prediction, I have the ability, using these AI techniques, to suggest to you to buy certain things. And by doing that, they created a P&L of one. They look at that model and they focus that model exactly on you with the right ads, and they create the ability to generate a certain type of P&L. So a model of one to a P&L of one, then they put it in a platform so I could reuse it a lot quickly, a lot cheaper. And they went from books to general retail, from general retail all the way through to web services. Then they actually amped that model up on steroids. They give you a Kindle so they have information on you in terms of getting that information very quickly. Then they put Alexa in your homes and you speak to Alexa and they collect all the information they need. A much better model of one. All going to a P&L of one. All going to a platform of one. And Google and Amazon uses the same techniques. Google and Apple uses the same techniques as well. So we took that as a basis. Could we apply the same things to assets? So the jet engine, for instance, what we normally did was we collected aggregate information about it, fleet information about it. So rather than do that, could we collect information about an individual engine, an individual asset? Could we look at the design of the asset, the manufacturing of the asset, the way it was serviced and operated, collect all that information, where it flies, the environment it flies in, create a model of one, which is what we did. Then normally we apply fleet analytics. How fleet analytics work is what I do is I make assumptions. I say I assume this jet engine is going to fly between these types of cities in this temperature, in this pressure, in this contaminant level, and based upon the way it's operated, it accelerates or derates at a certain speed. It actually climbs at a certain speed for a certain distance. Based on those averages, I can assume this parts in it would last 4,000 cycles or 4,000 flights. Or I can assume this is the fuel efficiency I would get. But now I can get the actual data. Now I know exactly the cities it flew between. I know exactly the temperature, the pressure, the dust contamination level. So with that, and the way it was flown, exactly the derate it took off at, how long it cruised, how long it climbed, I can predict this part exactly would last 4,000 or 6,000 flights. So now I don't need to bring it back in every 2,000 flights to change that part on average. I can tell it exactly when to come in. So I have prolonged life. I have changed the economics around life. Also, I can look at where it's flown. I can tell you, with the contaminant levels between these cities, there's going to be a buildup of contaminants on the blades that spin, reducing the aerodynamic capabilities, and so it gets less fuel efficient. So I can tell you when to go have a wash that will wash off those contaminants. So if I change the life of the part, or when I bring it in, and I change the fuel efficiency, I change the economics. I have a P&L of one. So I go from a model of one to a P&L of one, I put it into a platform, and I can apply the same thinking from jet engines to gas turbines to wind turbines to the parts inside of our healthcare devices. And this is the journey we went on using that technique, and we call this the digital twin. The capability here is to take that deep knowledge I have of the physical asset, the design, the manufacturing, the service, and the operation, the physics of it, and I combine it with the data and AI techniques, and I create this living learning model. Why is it living? Normally we create models in the design phase, we create models for services when we have a big problem. But what if when I have those models, I continually update it? Every time that engine lands, I pull data off that engine of how it was operated, where it was flown, and I tune that model. The model becomes a living model. What if I look at this asset and I compare it to others that are flying in the same way, the same pattern on the globe, and I say, can I learn from what's happening to them? So now I have a living learning model, and it's personalized to this asset. With that living learning model, combining the physical and the digital, I can get insights. I can get insights on the remaining useful life of a part. I can get insights on the efficiency. But insights don't generate value. You have to literally do something. So you take an action. I can say, okay, now you bring that in for service, or you don't need to bring that in for service. Now you actually have to do a foam wash to clean the asset, so I get better efficiency. With those actual actions, I get value. I can see the efficiency after I clean it. I can look on the next flight and I can see the value of the fuel efficiency I get. I feed that back into the twin, so the twin begins to get smarter. Every cycle, the twin learns. Then after I collect enough information, I have information I can use in the design. I can create a better design and feed it back into the system. So I have this living learning system using the physics and the data called a twin. Now with that, how do we extract value? We extract value in 3 ways. I can give you early warning on a problem. This is a compressor problem on planes. Usually this happens maybe a day or at the gate. A light shows up on the dashboard, the flight is delayed, or the flight is no longer happening. So I have to move all these people off the plane. Now I can get that information 30 days in advance. I can take an action so that I have that asset available. It can generate money. The second column is continuous prediction. I can predict the damage on a part, and I can know exactly when to bring that asset in. I don't have to bring it in every 2,000 flights. I can tell you the asset should come in every 4,000 flights. So because I do that, I allow the asset to have greater availability, the customer makes more money, and I bring the asset in at the right time into the shop, and I use the shop in a more efficient way. So I can generate more money for the customer. I can use the shops which reduce outage times more efficiently. Last thing I do is dynamic optimization. I can look at your fleet. You have routes that you have declared. When you have a flight agenda, you say, I'm flying on these routes to Dubai, I'm flying on these routes to Buenos Aires. I can tell you which assets to fly on this route. Because if you keep one asset with one set of engines flying on a route into a hot and harsh environment, that will wear out quicker. So I can show you how to balance the assets where they fly. If you balance the assets in the right way, I need to have less spare engines, or I need to have less engines that I lease when those engines are in the shop. So I can actually give you optimization of your fleet to reduce your leasing cost. So these are the 3 ways we capitalize on value. Over 2016 to 2017, in GE, we have built 1.2 million twins, generated $580 million of value. The power of the twin is the ability for it to live and to learn. How do you do that? How do you make sure it continually gets enhanced? Well, what we do is we actually find ways to collect ground truth. So if you start in the middle, I build a digital twin that predicts the life on this coating. We're thinking about this damage that is on the blade. How do I predict what the damage is going to be on the blade and bring it in at the right time? Well, what I do is when I do bring it in, I actually have an AI system that can look at that blade and determine the damage on it. It's called sporulation. So when you fly in these hot and harsh environments, contaminants fall on the blade. When contaminants fall on the blade, what occurs is these eat in to that layer that you have that protects the blade on the outside. So if I can actually predict when this thing is going to actually come out or sporulate and the size of it, I can tell you when to bring it in. But when you do bring it in, I need to get that ground truth. I need to know, was my prediction correct? So normally what you have is you have a person go into a dark room, cleans the blade, puts on a certain coating, and then uses a UV light in a totally blackened room to look for damage. They do that 8 hours a day, 5 days a week for 4 years before they get good. What you find out is on Mondays and Fridays, we have the worst results. It's a human being. Now we have a computer vision system that looks at this, and with computer vision, we can actually have the system figure out exactly where the damage is, get the actual measurements of where the damage is, reflect on the fact that the last time it came in, the damage was this amount, now the damage is larger, feed that back into the digital twin. The digital twin gets better. So you see AI in the distress ranking, AI in the digital twin capability, and then we actually can create a new coating. We can give that back to the designers and say, create a new coating for me so that that coating is better. This is how you improve it. Constantly learning, living algorithm. It's, do I have a brain in my body and I'm getting my brain better by feedback? What else can I do? I can create an immortal machine. This is the new journey we're on. How do I do that? What I do is I say the twin is not only giving me information about the coating. Suppose now the right thing to do is to design an entirely new blade, an entirely new part that, because I can shape the part differently, given the environments this flies in, given the stresses on it, I can create the perfect part so that I can get longer life and better performance. So the analogy here is the human body. I'm continually getting smarter by learning from my environment and by learning from people. That's a digital twin. I'm continually replacing body parts so that when those parts get updated, I get better limbs, lasting long and performing better. This is the journey that we have inside machines to give you the capability to create an immortal machine. But to do that, you're going to need additive manufacturing. Because to do that at the right cost for each individual machine, you will need this additive capability. And there, at the edge, when you build these capabilities, you have to embed that AI capability to do that. In that tiny machine that we have down here, not so tiny when you look at it in a room, but compared to a jet engine, that's where the power is. So I'd love to invite Brent Brunel to talk about how we do that inside this additive capability to build this immortal machine.
Great, thank you, Colin. Good morning, everybody. What I'd like to do is, Colin talked about kind of larger framework, mature areas where GE's been working. I want to focus on additive manufacturing and dig down to the details of what needs to happen on the edge, where we're working right now. So this is not an answer, this is a current status of where we're going. What I'd like to do is first talk about additive manufacturing. And a great example from GE. So GE has both the additive manufacturing business, so we sell metal additive manufacturing machines. We also are a practitioner of using additive to help out our products. A great area is this aviation. So this is a part from a T901 engine, so this is a helicopter engine. This engine is the successor to the T700, which has been running our Blackhawks since 1979, so this is a long-running engine. The Army wanted to get 25% more fuel burn, so better fuel efficiency, and get a certain percentage of weight out of the aircraft. We were able to use additive technologies as a big differentiator in this competition to help us meet those requirements. So we won the award. And this is an example of one of the parts inside of the engine. So previously, this is a mid-frame assembly. So this is where in the center of it would be a shaft. On the outside would be where the combustion is. So there's a lot going on in that part. In the past, that part would have been 300 parts. All right, so that consolidation from 300 parts down to one part, big change for the industry. And people have heard maybe that part of the story before. What's interesting is it's not just part consolidation and getting some performance. It's also, that used to 300 parts was 300 suppliers with 50 different records that you had to keep track of to do all those things. The other part is the engineering. Used to take 60 people to go do this. This was 6 to 8 people. All right, so I want to get everybody around the idea of, for additive manufacturing, it's not just disrupting and making better parts. It's disrupting the supply chain, it's disrupting manufacturing at large, and it's disrupting engineering too. All right. What I want to talk about from the AI point of view is, I want to focus us down to a core area of the additive manufacturing process. So the machines that we make these on are what we call laser bed powder machines. So essentially you have a powder layer of metal. You take a laser beam, it hits that powder metal, melts it, it solidifies, and you slowly build up the part, kind of particle by particle up to what you want it to be. That area, right where that melting is where I need to have AI help me out. I want to walk you guys through a lot of details of how that works. Okay, so those dynamics, I guess one lesson learned from GE. So this was a big conversation we had about 5 years ago was, what things should I run from the cloud and what things should I run at the edge? The chart on the upper left-hand side here tries to talk about what we call this Nyquist criterion. It is, how often do I have to sample something if I want to be able to see its behavior? And the idea is, on the left-hand side of this is slow natural frequency, so big things, big slow things. Right-hand side is fast things, so usually electrical things, very small mechanical things, those kind of things on the right-hand side. And the idea is, let me give you an example so you get a feel for this, right? And I think there's a surprising result. Even when we look at something very big, like a wind turbine, our wind turbine blades are 100, 120, 130 meters long, bigger than a football field. The natural frequency of that blade is about 1 hertz, okay? Nyquist's criterion says, for me to see the movement of that blade, the dynamics of that blade, I need to sample it 2 times per frequency. Okay, that's maybe not too bad, so twice per second I can do that. So that lets me know I can see it moving kind of correctly. If I want to see how it's moving, the rule of thumb is I want to sample between 10 and 20 times per second. Okay, so now you got something that's as big and as slow as this wind blade that's bigger than a football field. I need to sample it 20 times faster than 1 second, so 50 milliseconds, right? So even for a really, really big system, I need to sample it at 50 milliseconds to be able to watch and understand its behavior from a safety critical point of view. Okay, so from a GE point of view, we have other systems on here. So on the right-hand side is things that are really fast. So like an electrical converter where we're moving current around a circuit. Those are in the 10 kilohertz range, right? So that gives you an idea of the areas that we're working on. For additive, that main frequency of that melt pool is about 1 kilohertz. Okay, so for me to be able to see what's really happening in that melt pool, I need to sample at about 10 to 20 kilohertz, so 10,000 to 20,000 times per second. I need to sample those things. So very fast versus what we've had to look at in the past. The next part is I need to look at that melt pool. I need to understand a lot about it. In the past, I would have done a thermocouple or maybe a speed or a pressure. Each one of those would be about 32 bits, right? It could be anywhere from 4 bits to 30 bits, depending on your A to D. All right, so maybe it's hundreds of bits per sample. Now I want to look at very dense kind of image of that system. Now if I'm at a high density camera, right, this is millions of pixels times 8 to 16 bits per pixel. I'm in the tens of millions of bits per second. I went from hundreds of bits per second to tens of millions of bits per second. All right, and the last part is, okay, now I'm sampling it fast enough so I can see it. Now I want to go run my algorithms. In the past, it was I had rules-based, or I had, kind of simple model-based. We're moving to the deep neural nets to help us be able to see all of this. And the order of magnitude here is those deep neural nets, I need to run, it's tens of gigaflops per sample, right? So from my point of view, this is the perfect storm, right? I have to do this incredibly fast. I have to bring in more data than I've ever had before and have to compute more than I've ever had before to be able to see what's really going on in this melt pool. What I'd like to do is walk you through what's happening in the melt pool. This is, my point's a fun part. So we have a simulation. Let me tell you about it because it goes fast when I hit the button. The simulation, I first just show a video of laser hitting a powder bed, just so you see the laser and how fast it goes. And when you see that laser, if you think about, God, I can't see a lot going on there, right? Then what I do is I show a simulation of the laser hitting the powder bed, and it shows you all the dynamics, and I run it 1,000 times slower than real time. Then I run it 20 times slower, then I run it 2 times, and I run it real time, just so your brain can get a feel for, when I see it real time, you can't see anything. But if you back it up to that 1,000 times, that's what I really need to see with my AI system to help me understand the quality of the parts. So let's get this to go. Okay, so here's just the lasers, some typical examples going across the part. Now what I'll do is I'll bring you guys and show you this simulation. So that blue part is the powder bed. This is the laser coming down and hitting the powder. It's just starting to melt it at this point. What you can see is an indentation. It's moving from left to right. It's starting to melt the powder on the right-hand side. It brings the fluid through. It's all liquid flow on the backside. So this has evaporation, this has melting, this has convection. This has a lot of the different physics in this. And what you'll see is there's the flow that's coming through to the backside. The red is still liquid. And then as it's solidifying, it's turning to green. So it's cooling on that side. The other interesting part is it doesn't just go through that single layer, is that the laser actually penetrates down to the layer below it. So you're actually impacting prior layers that you had put down and had some weld of the material as well. You can also see some pores. Those are things we're trying to avoid as you do these. So we try to come up with the right kind of strategies to run those things. I'll just run it out for a couple more seconds till it gets to the end. And then we'll watch it as you turn off the laser, we'll watch it cool. And even just the cooling part, from my point of view, is interesting. It's not a uniform cooling. And cooling rate is one of the most important factors in the material properties that you get. So the laser's off. Now you can see it's starting to solidify. The green is solid materials, solid metal. And it cools down in these kind of pools. So each one of those is going to get slightly different grain structures of the material. So now what I'll do is I'll take it and I'll run it faster, just so you start to get a feel. It's still the same simulation. So that's 20 times faster, 2 times, and then close to real time. So all that dynamics is really happening in there. You can't see it unless you're measuring it at 10,000, 20,000 kilohertz, right? So those kind of numbers. Okay, so I just want to walk everybody through. So that's what we need to see. That's what I need to have the AI system give me insights into. Okay, so what we did is we set up a system around our machine. So we're using a camera. That camera's taking images on the order of 10 to 20 kilohertz. We ran lots of different parts with lots of different control settings to get training data for it. We ran about 10 million images through the system. We're using TensorFlow as our framework. We started off with an Inception V1 form for the neural net. We've modified that a little bit. And we're starting to see, so we ran it on NVIDIA DGX. That's where we did our training. Took us probably on the order of 48 hours to run all those simulations through. And we're getting great results. So out of this, we're getting on the order of 85 to 95% we call accuracy of those quality parameters. And those are things like what's happening with that melt pool, how wide is it, how much energy we think is getting pulled into it, how long is that tail, how long is it taking to do the solidification, is giving us great estimates of those things. So this is working out pretty well for us so far. So that training side and our initial simulations are working out. Where we're still working, and this is to the crowd here, is doing the inference on the edge, right? So pulling in that much data, running it through that many calculations is where we're trying to work right now. I'd say some of the things that we're trying to get done is, hey, we want to be able to run through this entire system much faster than it takes right now from development to deployment on inference. So first step is how do we get interoperability among the frameworks, the neural net frameworks? How do I use tools and capabilities across them? The next part is I need to be able to use these accelerators to be able to deploy it onto the hardware. How do I get it so I can use those faster and get it so I don't have to learn a different deployment tool every single time? And the last part is getting to that performance. All right, so on the right-hand side is where we're at today. So we've been able to use OpenVINO as our tool for deployment to getting it on these different Intel platforms. At this point, our current status is we're running about 2 kilohertz, so 2,000 frames per second, running that entire process. We need to get to 10,000 to 20,000 is where we need to go, right? To be able to see all that stuff and be able to react correctly for us to move forward. So this is our journey. Love to hear from people in the room on ideas how we can move this forward. We actually have Joel Markham over on the side here is helping us to try to get that there. So, okay, so the idea of this is if I can do this, then I can see the quality. If I can see the quality, we're hoping that we can figure out how to essentially control it and get it to where we need to go. That's one of those key steps on the journey that Colin was talking about, is to get to this immortal machine, get to this ability to update the design from data, update the part, put it back in the machine, watch it, see where it's going to go. All that depends on our ability to come up with essentially a just press print capability. I press a button, out comes a part exactly as we want to have. That's where we want to go. And I think we just want to share that quick journey with you and share where we're at with the AI on the edge at GE.
Thanks, Brent. We'll take a couple of minutes to see if there are any questions for Brent and Colin. Any questions, anyone?
How do you validate that the model, the image model that you're seeing, actually correlates to the quality of the solidified melt?
Yeah, so there's
The mic, that's okay, no worries.
Yep. Thank you. Sorry. So there's both just initial testing. I don't know why I'm getting the echo, but there's just initial testing of we run all these parts, we get the parts out, we do some initial just image screening of them. But then what we do is we take those, we actually do cut-ups of those to get material properties off of them. So we take those material properties and take those and compare those back to what our estimates were from the neural net, right? So those are real results, kind of quantified. How do they compare to those? Put those together to see how we're at from an accuracy point of view. So that's how we get to the results, validation of them.
I'd like to talk
Oh, please.
about whether the material property tools you have are appropriate for
Oh, we'd love to. Yeah. So GE's obviously doing a lot of work in that area, so I'd love to talk about that. Yep, please. Yep.
Thank you.
Yes, please.
So you mentioned you have issues at influence time, but you want to go faster. So which level you are at now and where you want to go?
Yep. So currently we're running on our FPGAs. The question is, so we think there's probably a couple steps to take on the algorithm side still, but we're going to hit a point pretty soon where I need more computation. I need some more hardware solution. So we're looking for ideas on what are the other solutions we can get. We're at the research point with it, so we can still spend reasonable dollars to go build an experimental rig. But in the end, the solutions wants to be less than like a $10K solution, $10,000 solution, right? So experimentally, we can still play around and figure out a solution to this, but then I have to figure out what is the way to get to an industrialized, productionized version for us to use moving forward. So. Yep, please.
How long has it taken you to get to where you are?
Yep.
So is this a decade-long process or years?
Yeah, so I guess at the larger one, this has been on the order of an 8 to 10 year journey. So this one particular additive one has only been 6 months to a year or something on this piece, right? So this larger journey has been about a 10-year journey for GE, starting with our digital initiatives back in 2010, 2011 timeframe. So this has been work we've been building up on that since then. So. Yep.
Any other questions, anyone? All right.
Perfect.
Thank you very much.
Yeah, thank you very much. Appreciate it. Thank you.